Hey everyone. So in this part of the video, we will talk about proximity analysis, generalization, and spatial overlay. So the first one we have is buffering, which is a type of proximity analysis. We use this to identify areas within a specified distance threshold from a given location. So for example, we want to identify the service area of different hospital. We can create a 5 kilometer buffer around each hospital, uh, assuming that anyone within this buffer can access the hospital services. Please note that to create the buffer, the spatial measurement must be in linear units, and we can achieve that by converting the coordinate reference system into the projected coordinate system. So for example, in our case, let's check the CRS for hospitals, and you can see that it's in a geographic coordinate system, and we can convert it to a pseudo-marketer EPSG 3857. So this is the projected coordinate system that is commonly used across many popular mapping platforms, for example, Google Maps, Apple Map, OpenStreetMap. And this projected coordinate system estimate the distances in meters. So to create the buffer around each hospital for 5 kilometer, we can call this buffer function. And inside the parenthesis, we can put 5,000 meter, which is equivalent to 5 kilometer. And one thing to note that this buffer option will return you a geoseries, not a geodata frame. It is only showing the polygons uh, objects we created around each hospital location points, and it is a geoseries. Here you can see um, the buffer we identified. However, so here you can see that the type of the hospital buffer, it's showing it's a geoseries. However, like converting this geoseries into a geodata frame is very easy, and based on everything you learned so far in GeoPandas, you should be able to do that very easily. In the next one, so we will learn about generalizing multiple spatial datasets, more granular datasets into simpler geometries. So we can use the dissolve function for that purposes. Within this dissolve function, we generalize the data by aggregating geometric properties based on its attribute values. So within the dissolve function, we merge geometries into single geometries if they share the same dissolve attribute values. On top of that, we can also aggregate remaining attribute values by specifying an aggregate function. For example, say we do not want the Virginia boundary data at the tract level, but only at the county level. So in this case, we can dissolve to merge the tracts into counties, and we can also calculate the average tract size for each counties. So the first, we will convert the VA tract data to a projected coordinate system so that we can calculate the area. Here again, we are converting it to EPSG 3857, and then we are calculating area of each census tracts located within Virginia state. And after that, we are creating a subset of columns that we need for the dissolve process. So we need the county FIPS code so that we can dissolve the geometries based on this county FIPS code. We also need the geometries, and we also need the area column so that we can calculate the average tract size. And then here we call the dissolve function. We are saying that dissolve it by county FIPS and aggregate the area measures or all the other attributes based on their mean values. So this is the output you can get. So in this output data set, you can see that we have 133 polygons, each representing a county within Virginia. And this area kilometer square, it's saying us the average tract size for each county. And here you can see the dissolved boundary areas. So in this plot, you can see the boundaries only for the tracts, not, sorry, you can see the boundaries only for the counties, not for the tracts. The last thing we want to talk about is spatial overlay. So spatial overlay is very similar to spatial join. In spatial overlay, we also combine two or more spatial dataset. However, there's a key difference. In spatial overlay, we create new geometries based on the overlay operation. We can choose to intersect, union, identify the difference, and based on this spatial operation, it will create multiple geometries or combine geometries together. And a spatial overlay is more appropriate when we want to join polygon with polygons, line to polygons. So this type of merging is more appropriate. On the other hand, for spatial join, we only merge attributes from one dataset to another based on their spatial relationship, but we do not modify the geometries. And this is more appropriate for point to line or point to polygon merging. So for example, if we perform spatial overlay using intersection between this square and this circle, so you can see only this green area is the areas common between both layer. And after performing the spatial overlay, it will only return us the common areas. For union, it will merge both layers and keep all areas from the both dataset. For symmetrical difference, it will keep the areas that are either that are in either layer but not in both layer. So partially part of this square and part of this circle, but not this middle part. And lastly, when we use the difference operation, it will return the areas that are in the first layer, but not in the second layer. So with spatial join, this modifications does not happen. We only merge the attributes, but it does not modify the geometries. And here you can see an example. We want to merge uh, the park locations within Fairfax County with the tract dataset using spatial overlays. So first we can retrieve the Fairfax County Park dataset from this open data portal. So again, we are using a GeoJSON link, and then even for spatial overlay, you must need to match the CRS. In our case, you can see the CRS do not match, so we need to convert them. We are converting the park CRS similar to the track CRS, and then we are overlaying both dataset. So we are overlaying the park dataset, and we want to identify which park is located in the particular track dataset using the intersection operation. So you can see it returns only these two geometries, these two modified geometries, I must say, that is located within our specific census tract we defined earlier. And if I plot them, you can see like these two tiny red zones, red polygons. So these are the ones we just identified through this spatial overlay intersection process. Now, here is another example of spatial overlay using union. So this is more appropriate when we have spatial data for side-by-side locations and we want to merge them together into one. So for example, in this case, we have road data for both Fairfax County and also Prince William County. And we want to combine these two road data set. again, first check the CRS and then you can use the union operation. And this is the output where you can see the road dataset for both Fairfax County and Prince William County. All right, so that's all I have for this entire topic, spatial operations with Shapely and GeoPandas. If you have any further question, please let me know. Thank you so much.